So again, I assume some of this is review, probably for all of you, but a little bit of it is just to establish some notation, and we won't spend too long on it. But again, the things I like to emphasize is about how we can work mostly with the loop gain L, right, when we're talking about stability. So you're probably familiar with the methods for analyzing stability in terms of Bode plot, right? So there's an example Bode plot sketched here for L, where we've labeled our unity gain frequency omega t, right? It's the frequency at which the magnitude response of L decreases to 0 dB, and the phase response shown on the bottom. So, we define the phase margin over here at the unity gain frequency omega t, the distance between the phase response of L and 180 degrees. But I always like to remind people where that comes from. It comes from a Nyquist stability criteria, which has a couple of assumptions underlying it. So for all the basic circuits that we're going to talk about in this course, probably all the ones you've talked about until now, and all the ones we're going to talk about in this course, this understanding of the Bode plot is fine, right? Basically, we define phase margin and, if you like, gain margin in the usual way, and we can infer a lot of useful practical information about the closed loop amplifier response from those things. But for more complicated feedback circuits, which I find are becoming more common in nanoscale CMOS technologies, where transistor gain, the intrinsic transistor gain, which we talked about before, is not that high. So because of that, people are having to use more transistors, basically more stages, in order to get a lot of gain. And so feedback loops are getting more complicated sometimes for some applications, which means that I think it's kind of becoming increasingly important to have a little deeper picture in your mind of stability, something that goes a little bit deeper than the Bode plot, understanding what's behind the Bode plot, because sometimes the Bode plot's not actually giving you enough information. It can mislead you even. So we're not going to do any of those types of circuits in the course, as I said, but I just want to take the opportunity before we go into the simpler first and second order feedback systems to remind ourselves the underlying Nyquist criteria, right? So basically, when you have a complex function like L, the way it works, you draw, you draw this contour in the complex plane, which is drawn to encircle the entire right half plane. And the idea is that by doing that, any of the mapping, when that contour is mapped through the function L, it will encircle the origin a number of times equal to its zeros minus its poles, right? The number of its zeros minus the number of its poles that are inside the original contour, okay? So even if you're not 100% following that, it's okay, because I want to, I think there's enough that I mentioned there that allows you to understand the very first assumption that underlies our sort of normal undergraduate level discussion of feedback for electronics, right? So I said right there something about the Nyquist plot will do some encirclements that depend on the number of zeros minus the number of poles, right? We always assume that the number of poles in L is in the right half plane is 0, right? So therefore, the number of encirclements we get has more to do with the number of zeros in L, okay? So that seems a little strange, but zeros in L will turn to, we're going to turn those into poles in the closed loop response. But the key point there is that when we count those encirclements, we're assuming that there's no right half plane poles in the original L, which means that the open loop response L is stable to begin with, right? If that's ever not the case, then all the stuff we're talking about is kind of off the table, right? But for all the, again, the stuff we're going to talk about, we've got amplifiers with high gain at DC and then 1 or 2 poles, and the gain starts rolling off. And so, L is clearly stable on its own, okay? It's only when we put it in feedback that we can get into troubles, okay? So So, rather than being interested in encirclements of the origin, we become instead interested in encirclements of the point -1, because what we really care about is not the zeros of L, but the zeros of 1 plus L. Because whenever 1 plus L becomes 0, the closed loop response, right, is going to blow up on us, right? So that's why what we, the Nyquist criteria, what it boils down to for the particular case that we're interested in, where L is stable to begin with, is that we want to make sure that this contour that we get by passing the whole j omega axis through the function L, we want to make sure that that resulting contour never encircles the point -1, because if it does, that means that 1 plus L will have a 0 somewhere in the right half plane, which means that ACL will have a pole somewhere in the right half plane and will be unstable. Okay, so we're always trying to make sure that this contour here does not encircle the point -1. So what is this contour here? As I said, this is basically the j omega axis, the whole axis pushed through the complex function L. Right, the frequency response, complex frequency response of the loop. So that contour is nothing more than the set of points that are the magnitude of L and the phase of L, right? As a function of frequency, we trace out this whole thing. What's not captured on this plot, it's kind of nice. It's showing us the magnitude and the phase responses simultaneously, except we don't know what value of omega is required to make us sweep along here, right? Like, we don't know what value of omega corresponds to this point versus this point. It's not captured in this plot. The Bode plot tells us that. It shows those two plotted separately versus frequency. But the Nyquist plot does tell us whether or not at any point in frequency does it encircle the point -1. And we want it to not do so in order to be stable. Okay, so then from that picture, we then derive the phase margin. We assume again, here's where we get into some more assumptions that are sometimes violated in more complex circuits. The phase margin is defined by the point where the magnitude, I'm going to zoom in even further here. We find the point where the magnitude of L becomes unity. Okay, so that's going to be wherever this contour here crosses through the unit circle, by definition. And then at that point, how much phase do we have? What's the phase angle L? And how far away is it from -180? So, and we use that again to infer some stuff about the dynamics of the closed loop amplifier. Now, the cases that we're interested in, the simple ones in this course, have magnitude response for L that looks like this. It basically decreases monotonically. But you can imagine that if there's some bumps in the magnitude response, you can get a much more complex case. You could get, this guy could go back out again, right? And this would be really, this would be a little bit confusing, right? How would we define the phase margin at this point? And you say, well, that's easy. I'm going to define the phase margin, I'm going to keep zooming in here, and I'm going to say it's got to be this one here, right? Because that's the one where I'm the closest, right? And that's how close I am to instability. Okay, fine. Now what if you have a system that does this? Okay. That's going to really kind of blow you away, because you're going to say, well, over here I've got a gain greater than 1, and I've got a phase that's more than -180. So that's it, I'm finished, I'm unstable. But in fact, you're not, right? When you look at the Nyquist plot, that thing never encircles the point -1, and it would be stable. So these are the types of feedback systems that are actually, as I said, they actually pop up, okay? And where all the stuff that we're gonna talk about from now on does not quite hold anymore, right? You're not gonna, even though we're not gonna present examples, that I always feel bad sort of telling you lies, especially at this point when you're in grad school, right? I mean, it's fine in undergrad and introductory course, and okay, half of these students are never going to need to know about this special case, but you might encounter this, and then you're going to think, oh, that prof lied to me or whatever. So yeah, some of the stuff I'm going to tell you, there's only certain circumstances where it's valid, right? And we're going to focus on those circumstances for now. But okay. So having said all that, here's a just laying out the definitions. The unity gain frequency is the frequency at which the loop gain is unity. You'll notice that the notation, right? I mean, sometimes I'm a little loose with the notation. I'm writing, for example, here, I kind of alternately write L as a function of the complex variable S and as a function of frequency omega. Strictly speaking, I mean, there should be a J in here, right? But I'm presuming that you'll be able to figure that out from context, okay? I just use the same function L in both cases. So, and the phase margin, right, defined here. And now I'm going to go back to something I mentioned before, that, I said that the closed loop response, remember we sketched the closed loop response alongside the amplifier response here, and we said, well, the closed loop response sort of maintains its desired or ideal value up until you get to the unity gain frequency, and then it starts following the open loop gain of the amplifier. Because basically, the intuition there is that beyond omega t, the loop's kind of open. You have no loop gain, the loop's kind of open. So what gain do you see? Well, you just see the forward gain of the amplifier A beyond that point, right? So that kind of makes some sense. But I mentioned before that there's some weird stuff that can go on here. So now that we've defined unity gain frequency and phase margin, we can say that L at omega t has a magnitude of unity and a phase, that's related to the phase margin. I can say it's negative e to the j theta. Okay, where theta is the phase margin. Okay, so that's just by definition of phase margin and by definition unity gain frequency. That's exact, right? So if I want to find out what is the actual closed loop response, this green line, evaluated at the unity gain frequency omega t, it's no problem. I just plug that in to our expression 1 over beta times L over 1 plus L, right? I plug in for L over here into that expression. And I end up with this over here. So now it's clear what's going on in the denominator here. We don't just have, in the past, the way this cartoon sketch here was drawn, we were kind of saying the denominator is 1 plus L and L is 1. But L is not really 1. L has this complex phase, which means that depending on the phase, the denominator may be less than 2, right? It'll probably be less than 2. So if what I'm trying to sketch up here is the magnitude response of the closed loop gain, I have to take the magnitude of this expression here. And when I do that, I find it depends on the phase margin, right? So there's a 1 minus cos theta in here. Oops, jumped around there. So, So if you look at that expression, it shows you that if you have less than 90 degrees of phase margin, then this term in here becomes less than 1. And so you start having, if I zoom in on this picture, here we draw this, right? You start having this response here gets bigger and bigger. Once that term becomes less than 1, then this starts getting nudged up. And in fact, if theta is less than 45, you actually start getting this. Okay. So it doesn't change the behavior out here, and it doesn't change the behavior out here. But around omega t, you have this function describing what the magnitude response is right at omega t. Okay. So this brings up an important kind of takeaway point. Okay, here's the sketch of that happening. You know, I think you get an impression just from the names that we use, phase margin, and when you look at this Nyquist picture even, right, you know, we talk about the phase margin being defined in this way, gain margin. You have this probably idea in your head that all of these things are just sort of a safety margin for stability, right? We're just really, really scared of being unstable, so we want a bit of margin there, right? That's what the word margin means. But when we specify in an assignment, or when your boss tells you you need a phase margin of at least 60 degrees, you need a phase margin of at least 80 degrees, that's not because he's being super paranoid and conservative. It's actually a performance spec. And this is the first example of that we're seeing, right? It's not hard to imagine that you just may not want that kind of closed loop response. You just don't want to see that peaking. You don't expect, if you're designing an amplifier, to have a gain of 10. You don't expect that all of a sudden at some high frequency, the gain goes up to 15. That's maybe really undesired and may cause big problems. And now we know that in order to avoid that, you need a phase margin of at least 45 degrees, right? It means that even if you have a phase margin of 40 degrees, you just think, oh, I still got tons of margin. No, but you're already causing a problem in the system. Something might break because of that. So, sorry for that kind of long digression, but again, I just want to drive home the point that phase margin is not just margin. It's a spec, right, that you have to hit. And then, sure, let's say we want to ensure that there's no peaking in the frequency response. So that would require us to be more than 45 degrees. And then maybe on top of that, we add a little bit of margin. Okay, we say, okay, we want 60, and we want 70. There are other specs for which we absolutely need more than 45 degrees, though, which we'll talk about later. Okay, so the rest of the lecture is just to look specifically at the common cases of first order and second order feedback systems. And even though this may at times feel like kindergarten stuff, it's actually really important to, once you understand this stuff in general, then hopefully you just start seeing the single stage op amp, two stage op amp as sort of special cases of this stuff, right? I think that's an important way to learn it because you're going to encounter different kind of op amps when you leave the course, right? That are strange, but you're going to be your ability to just cast that into one of these models that's going to allow you to quickly understand the behavior, right? And design one. So first order feedback system for us is one where the loop response L has just one pole and no zeros, okay? So mathematically, L could have a 0 and it would still be a first order system, but when we talk about first order feedback system, there's no 0 in L. That's kind of important because, again, otherwise these Bode plots would look quite different. So if there's only one pole and we're presuming that we have a DC gain, a DC loop gain that's, you know, quite a bit bigger than 1. So we're going to get a Bode plot that looks something like this. At low frequency, we're going to have our high gain, L0. And then here's the pole frequency, omega P1. At omega P1, we've got 45 degrees phase shift. And then beyond that, we start rolling off at 20 dB per decade. Finally, intersecting with the unity gain frequency, omega T. That's the unity gain frequency of the loop. So it doesn't matter how far apart the unity gain frequency and pole are. We're always going to have at least 90 degrees of phase shift if it's a pure first order feedback system, because there's only one pole and each pole only introduces 90 degrees of phase shift. You take us back to the Nyquist plot. What does it look like? So here we are at DC. At DC, we've got 0 degree, L has 0 degrees phase shift and has a high magnitude. So here's 0 degrees phase shift with a high magnitude. We're far from the origin. Then as we start moving along, increasing omega, nothing happens for a while. We're still staying out here, very little phase shift. The magnitude stays high. Then we start getting to this part of the curve. what happened? We start moving this way. We start getting a 45 degrees phase shift. And the magnitude response, hasn't changed very much. So we're still up here somewhere. Then the phase continues to increase all the way to 90, but as we do that, the magnitude starts decreasing. So we kind of curve into the origin like this, and we never really cross past this line here, right? Because we never get more than 90 degrees phase shift. So that's what the Nyquist plot looks like. Key takeaway points are that the feedback amplifier is always stable with at least, and in the practical case, approximately pretty close to 90 degrees phase margin. Okay? Because if these guys are far apart, the phase response will pretty much be settled to 90 degrees. So first order feedback systems are not, they're not going to be, even for this the single stage op amp we're going to talk about, a first order model is not really sufficient to capture some of the important details of that. I don't want to give you that wrong impression. The reason we talk about first order feedback system is that there's some, it's the one that has the nice closed form, sort of back of the envelope expressions for estimating things like settling time and bandwidth and some things that we care about. As soon as we get to second order systems, the expressions are a little bit more complicated than what you can, as I said, sketch in the back of an envelope or do in your head quickly and easily. So the first order, it's always nice. The first order analysis is kind of the starting point to give you a ballpark of where you're at in the design. Okay, so assuming we have a DC gain L0 that's a lot bigger than unity, then the unity gain frequency omega t is basically just the gain bandwidth product. And when that's the case, right, we can make this approximation as long as we're above the pole frequency. So if we look just at the magnitude response plot, basically what we're saying here is that there's not much difference between the actual magnitude response of L and what we would get from an integrator with the same unity gain frequency. Okay. Sure, they differ at DC. An integrator has infinite DC gain, the real loop gain doesn't. They differ a little bit at DC, but a lot of what this pole frequency may be really low, so everything we care about is going on around here, right? These Bode plots, remember, are on a log scale on the x-axis. So this is most of the bandwidth up here, and in particular it captures the point around omega t where everything we care about in terms of stability is there. So that's why we often use this model. It seems a little strange to use an integrator, but the way to think about it, the only place that they're different, the integrator model and the real model, is at really, really low frequencies, where anyway everything's kind of fine and dandy at really low frequencies anyway. Everything's pretty ideal, so we don't care too much. So when you make that substitution, you get this nice simple response. Remember, this is 1 over beta L 1 plus L. So when you substitute in the integrator here, you multiply the top and bottom by S over omega t, you end up with this really simple first order response. Okay. And basically what it shows is that for the first order feedback system, you've got a closed loop response that's also first order, where the 3 dB bandwidth of the closed loop amplifier is equal to the unity gain bandwidth of the loop. Okay, so that's not, I'll just write it for emphasis, not the pole omega p1, obviously, right? So this frequency over here, there's another bit of notation, is going to be omega negative 3 dB. So when I write, hopefully I'll stick to that, but when I write omega negative 3 dB, that means the 3 dB bandwidth of ACL. So that's our closed loop bandwidth, and the time constant, since it's a single time constant network, the settling time constant of the closed loop amplifier is just 1 over that, or 1 over omega t. So it means that the things we care about in the closed loop response, its bandwidth, its settling time, depend on omega t and don't depend at all on the pole, omega p1, which is kind of interesting. Okay. Now, if we've got a second order feedback amplifier, this is the more practical case that we're going to spend a little bit more time working with. So again, a second order transfer function in general can have a second order numerator, but for our purposes, we're considering only the all pole case, which means the second order system has 2 poles, no zero. Moreover, we're focusing on the case where both those poles are real valued. Okay. Basically what that means is that we've got a loop response L that looks like this. Okay. There's 2 real valued poles, omega p1 and omega p2. And they're separated, a little bit in frequency. Even if they were a little closer together, still you would see a magnitude response plot that looks something like this. It's flat at really low frequencies, below omega p1, at a large value. Then we hit the first pole, and the magnitude response starts rolling off. If the 2 poles are separated by a decade or so, then you'll see a region of the magnitude response plot that drops at about 6 dB per octave, or 20 dB per decade equivalently. And then some later point you'll get to a second pole frequency, and then the magnitude response will start dropping faster. Now if these 2 poles, omega p1 and omega p2, are closer together, obviously that whole thing will smear together and it will just look like a curve. Now, if we generalize even more, right, there will be, the amplifier may have other third poles, fourth poles, and may have a 0 or 2. But we'll see that we're going to design, for the basic op amps that we're going to work with, folded cascode, 2-stage op amp, these terms are at higher frequencies, certainly above omega t. Okay, if they're not, we've probably got, we're either in a much more complicated situation or we're just going to be unstable. So when that's the case, we can kind of take the real response, which is maybe more complicated than this, right? It might have kinks in it, or I exaggerated it a bit, obviously, but even when that's the case, we're going to model it as a second order system. We're going to kind of neglect these guys, and we're going to just assume that there's only 2 poles, and we're going to choose the second pole value in our model so that it accurately matches the real amplifier response at frequencies that are around omega t, which is where we really care. Okay. So if that all sounds wishy-washy, we'll nail it down a little bit more precisely, like how we decide what omega p2 is a little later when we look at some practical cases. But that's the basic idea. That's why we focus mostly on the first order and the second order cases. First order is the nice, intuitive, analytical one, and the second order is very useful practically because even when we have a higher order response, we can model it as a second order response and get away with it. Unless you're in a very strange case. So that's why sometimes instead of omega p2, you'll see this as written as omega eq. That's indicating that this is an equivalent second pole. It's basically like a fictitious second pole that's just been chosen to capture the combined effect of 2 or 3 poles and a 0 or 2. Okay. So, here's our second order model, okay? And we can find the phase margin pretty straightforwardly by making this assumption. This is a bit of an approximation, but it's a very good approximation. As long as omega p1 is way less than omega t. As long as that's the case, then the phase contribution of omega p1 is going to be basically minus 90 degrees. And so we really only have to worry about omega p2. The contribution of omega p2, or omega EQ here, is that term, is just this arctangent function there. So that's capturing this shape over here. So then if we plug in omega t into that expression over here, and we take 180 minus that, this whole term, then we find the phase margin. Okay. So we can do that. This is 90 minus 10 inverse omega t over omega EQ. Okay. And then just, so this expression here is sort of an analysis equation, because if we know what omega t is in the second pole frequency, we could find out the phase margin of our second order feedback loop. And you'll see, key point here is that it depends only on the ratio of omega t to the second pole. Okay, that tells you how much phase margin you have. So I just want to kind of say that again. It means that how much phase margin you have, which is one of our main stability spec that we're going to work with, it doesn't depend on the first pole. It depends on the second pole, and specifically where that second pole is in relation to the unity gain frequency omega t. Okay, so we could do some simple cases. If omega t equals omega EQ, right? If the unity gain frequency is right at the second pole, that should be obvious, right? That means the first pole is contributing minus 90, the second pole is contributing minus 45. So then you'd have 45 degrees phase margin. For the reason we mentioned before, and also for some other reasons, usually that's not enough. Usually you want more than 45 degrees phase margin. So in order to achieve that, what does that mean? Do we have to make omega t smaller than omega EQ or bigger? Let's make it smaller, right? So whereas this is a sort of analysis equation that tells you the phase margin once you know some stuff about the loop, this is a key design equation. It's just rearranging this one here in a way so that now we see, let's say we have an amplifier with a second pole at omega EQ, okay? And we want to make sure that we have a certain desired phase margin. We need 60 degrees phase margin. So we can plug in 60 degrees here, take 10 to 30 degrees, and then we'll see that omega t has to be 3 or 4 times, I forget the number, it's on the next slide, 3 or 4 times bigger than omega EQ. Okay? And then we're going to go about and modify the design of the, basically we're going to stick a capacitor in there, or something similar, to do compensation so that we make omega t equal that value. Okay, so this is like this example. Let's say amplifier is a second pole of 50 megahertz, and we're going to put it in feedback with beta equals 1, and we need 45 degrees phase margin, right? We can figure out omega t has to be about a quarter of that second pole frequency, so we got to put it at about 13 megahertz. Okay, for 75 degrees phase margin. So that's one. So this is important design equation for compensating an amplifier. We're going to know omega EQ. We're going to have a spec on phase margin, and we're going to use this to figure out what omega t needs to be. The full analysis, as I said, for the second order response is a little bit more complicated, unfortunately, than it is for the first order response. First order response, everything was single time constant, real pole, boom, you know the settling time and all that stuff. Second order, it gets messier, but some key points that come out from all this is that it's possible, even with only real valued poles in L, it's possible to get complex valued poles in the closed loop response. That can be fine, except that if you have complex poles in a system that are kind of close to the j omega axis, you start getting some weird behavior. The closed loop response will have peaking, as we've already seen. Moreover, the transient step response for an amplifier, a closed loop amplifier with poles like this, let's call it the step response of the closed loop amplifier like this, as a function of time, it can look like this. That's also something we often, in a lot of cases, we really need to avoid that. So this boxed expression over here just tells you how much overshoot you get for a given value, for a given Q factor in these complex conjugate poles. And again, this will arise even if the loop is stable, even if you have some phase margin, but just not enough phase margin. You'll get complex conjugate poles and you'll get this ringing in the step response. So, this is a really useful table, again, for design, that relates a few different things. So these are a bunch of different phase margins that we could design our feedback loop to have. And assuming this is all only for a second order feedback system, right? This whole table which means that this whole table assumes that L has two poles and no zeros. Okay? If that's the case, corresponding to each of these phase margins, we can find out what the ratio of omega t to omega EQ needs to be. And that's just coming from this expression up here. Right? So we're just tabulating that equation here. Also tabulated here is that with that ratio of omega t and omega EQ, and with the corresponding phase margin, here's the Q factor for the closed loop response. Okay. And then here's the amount of overshoot that you get in the step response for the closed loop case if you design for this much phase margin. Okay, so this is really interesting. First of all, we saw already that if you want to avoid peaking in the magnitude response, you need to ensure a certain minimum phase margin. I think I said 45 degrees was enough. In fact, it's not enough. You need even a little more than 45 degrees to ensure there's no peaking. You need at least 60 degrees to ensure there's no peaking in the magnitude response, the closed loop magnitude response. And then you see over here from this column that if you want very little overshoot, you need more like 75 degrees phase margin. If you design the loop to have 80 degrees of phase margin, then actually you get monotonic settling in the step response, which means it never crosses over its final value. Okay? So again, if you want that kind of settling behavior with no overshoot at all, you actually have to have 80 degrees of phase margin. Again, just driving home the point, it's not just margin, right? not just safety and paranoia. It's that it's a spec that relates to important things about dynamic response that you care about. Okay? Yeah. So if you move this way, right? So let's say this red curve I drew, the red step response I drew over there is for like 80 degrees phase margin system. But if you take that same system and you increase omega t, then this ratio is going to go up. You're going to move upwards on the table, which means you start having some overshoot, but it does get faster in this sense. So if that's what you mean by faster, right? And, there's a little deeper point there that there's kind of a sweet spot here, right? Where maybe you overshoot once and then you settle, and maybe that is kind of faster, right? It depends on your definition of fast, actually. So, which is a good point you're raising. So let's say your definition of fast is you want it to settle to within X% of its final value, as fast as possible, okay? It actually depends, the phase margin you want then depends on X, okay? If X is really loose, then maybe I want one that rings a bit, right? As long as it stays within X, it'll get there faster. But once we start making X really, really tight, then that pushes us to higher phase margins, and because then we need the smoother settling. We actually get within that boundary sooner by not having any ringing if X is really tight. So it depends on what you mean by fast, like how accurate do you need it to settle. Yeah, so that's not, you're right, and that's not kind of captured here. And this is, and as well, I mean, I put no labels on this time axis here, right? Because everything here is kind of normalized, meaning that all I'm showing here is the ratio of omega t with respect to omega EQ. Obviously, if I am somehow able to double both omega t and omega EQ, I mean, I'm going to be twice as fast, and I'll be just as stable as I was before. So that's, if you like, that's plan A, right? But in terms of getting faster, a faster amplifier, but that would probably come at some cost, more power, or maybe you just can't even do it with the transistors you've got. There's too many parasitics, right? But so the idea is that a common case is that you do everything you can to make omega EQ as high a frequency as possible, given your power budget, whatever other constraints are put on you. Now you've done that. Now, what should I make omega t? I set omega t by compensation. Where should I put omega t? Well, my boss told me I'm not allowed any overshoot at all, so I'm going to have to put omega t, at about 0.17 times omega EQ. Unfortunately, really back way off. So this is this table has there's a lot of I think a lot of design insights here. One is that this really kind of illustrates the speed penalty, if you like, that comes from closed loop amplifiers versus open loop amplifiers. Omega EQ is kind of like some pole, right? We're going to see that that's a pole frequency in some stage of our op-amp, right? Some part of our op-amp has a bandwidth of omega EQ, but there's many stages there, so that becomes the second pole. So if you like, that's kind of the speed of a part of our op-amp that's limiting us. But if we put feedback around that thing, in order to keep it stable, what we're seeing now is we have to back off from that bandwidth by like a factor of 4, a factor of 5, just to make sure that the amplifier doesn't have crazy settling time and things like that. Okay? So you'll sometimes hear that referred to, that feedback comes with this kind of speed penalty. That's what it means. That means just in order to keep the thing stable, you have to kind of back off a bit from the poles, right, and compensate things to give you this between 60 and 85 degrees of phase margin. Because remember that omega t is somehow related, I'll draw it this way, to the 3 dB bandwidth of our closed loop amplifier. Omega 3 dB is our closed loop bandwidth. Now be careful there, because those two are equal for the single time constant case, but this whole table is talking about the second order case, right? Not the first order case. So that's why I drew a squiggle there, but they're related anyway, right? Omega t is sort of like the bandwidth of a closed loop amplifier, which means the closed loop amplifier has to have a bandwidth of like a quarter or a fifth of omega EQ. Okay. So this is just saying something that I talked about before. It's that let's say you have a higher order feedback system, third, fourth, fifth order. So one approach that you can sometimes take, and I'm choosing my words here a little carefully because there's, again, this proliferation of new amplifier topologies. They're not new actually, but they're become popular now again because of nanoscale CMOS and limited intrinsic gain. So some of these new amplifier topologies, defy all this analysis that we're talking about and require a sort of different set of analytical tools. But if it's just a matter of, there's not a clear dominant second pole, or there's not a clear second pole, right? There's two or three of them that are all contributing a bit. That will be the case in some of the amplifiers we talk about. That's no problem. We're just going to make an equivalent second pole that somehow approximates the effect of all of these all together. In this case, omega EQ might be pretty close to omega P2, but it might be a little bit lower frequency because omega P3 is already introducing a little bit of phase shift too. So this expression suggests one way that you might choose that equivalent second pole frequency, but that presumes you already somehow know all those other pole frequencies and the zeros. A practical situation is you might not know exactly what those poles are, but you can simulate the circuit and you see a Bode plot that has kind of like a smear here and a smear down here. So a very practical way is to look at that Bode plot and say, okay, where's minus 135 degrees? That's going to be somewhere. And it's reaching minus 135 degrees there because of the effect of a couple poles and maybe a zero. But I'm just going to approximate this by saying, fine, I'm going to take that as my equivalent second pole, right? Now my second order model will have a phase shift of minus 135 at exactly the same frequency as the actual amplifier. And, around there, I'll be pretty close, right? Up here, I'll have a very different phase response, but I probably don't care very much what goes on up there because by then L is really, really tiny. So the loop's basically open. So that's a nice trick. Just read it right off the Bode plot. Where do you have minus 135? Okay, that's my second pole, or omega EQ. Now, I go and compensate. I take omega t. I back off from omega EQ by a factor of 4 or 5 or whatever, based on this table and my phase margin spec. Right? I find this ratio. And now I know what omega t needs to be. And the last thing is to just stick a cap somewhere, or maybe a resistor, so that omega t is equal to that value. And hopefully I'm done. Right? So that basically summarizes dominant pole compensation. Right? This is a simplified sort of way of thinking dominant pole compensation. Obviously, if you can get to this situation where there's one pole that's at way, way lower frequency than all the others, then you've pretty much got a first order system with 90 degrees of phase margin. Okay. So you can do that. Let's say omega EQ is over here. You could just make omega t 10 times smaller. Fine, and then you're done. Then you have a single time constant response. You won't, there's a lot of cases where you won't want to do that. It's probably not a very efficient way to do things. Even if you only need a very limited bandwidth, probably there's a way to go back and re-optimize the op-amp so that omega EQ is not so high, right? Save some power, do something different there. So that, because if omega t only needs to be here, then I'm okay even if omega EQ creeps all the way down here, right? And I still will have 85 degrees phase margin. So you might as well do that. So that's why this is not, it may arise sometimes with like a really easy set of specs that anything will do there, but it's kind of an indication that there's some over-design somewhere. For second order system, here's how the compensation procedure will work. This is general, but again, once you understand this, then really it's just a matter of applying this to specific circuits, right? So here's your equivalent second order response. You have a certain phase margin spec, okay? From simulation, perhaps you've estimated omega EQ, and then you can find out what omega T you need. So this is the example from before. We find, okay, we need a unity gain frequency of 13.4 megahertz. So again, this is just emphasizing that it's really the second pole omega EQ in L that ends up setting the closed loop bandwidth, because the closed loop bandwidth is determined by omega T. So then what you go and do is you just drop omega P1 until Ft is equal to the desired value here. So here's what that looks like on a Bode plot. Let's say you start with the dashed line there. That's no compensation. Okay. So from this, and the phase response plot for the dashed line is shown down here. That's before you've done any compensation. You go and you find the frequency where this is minus 135. You say, okay, that's my omega EQ. And you say, oh, and you realize, okay, I require, what was the example here? 75 degrees phase margin. So because of that, I've got to put omega T over here. Okay, I've got to take omega T and shift it down here. So how do I do that? I do that by messing with omega P1. Right? That's already the lowest frequency pole. The lowest frequency pole doesn't really affect the closed loop bandwidth, right? Oh, sorry, I should take that back. We would not want to take omega P2 and move it back here, because now we would have a new second pole, right? That's even lower than the first one. I think that's a better way to say it. So it's natural that you would take whichever pole is already the lowest and just knock it down by introducing a capacitor somewhere in a clever place. So that's how dominant pole compensation is performed. You find that dominant pole, knock it down so that omega T shifts over to its desired value. And that gives you the phase margin you're after. Then finally, as a last step, you can perform what's called lead compensation to give you a little bit of extra phase margin. Lead compensation, I'll illustrate it here with a red pen, amounts to putting a zero at a frequency a little bit higher. The way we're going to use lead compensation is we're going to place a zero at a frequency higher than omega T, and a left half plane zero, then we'll introduce a positive phase shift. So it's going to take the compensated phase response here, the dashed line, it's going to nudge it up a bit because of the zero, and give us a little bit of extra phase margin. But because omega Z is above omega T, it will have not too much effect on the gain, the magnitude response. So that's a little bit, lead compensation is a little bit, I would say almost a heuristic approach that we're taking, in the sense that a lot of our analysis was based on this assumption of a second order L with no zeros. Then at the very end, we go and we stick in a zero. Right? So watch out for that. It sort of, in a sense, it invalidates that whole table that we're using for design. But the reason we get away with it is because we only use lead compensation, to provide a little bit of weak adjustment. We put omega Z above omega T, and we just try and get a little boost of 10, 20 degrees extra phase margin. And it turns out, it can be shown by a much more painful analysis, which I won't go through, that if you introduce just a little bit of extra phase margin that way, it doesn't introduce overshoot, it doesn't cause things to screw up. You know, all the good properties that we're after are preserved still. So that's the two-step approach, right? You find out how much phase margin you need. You do dominant pole compensation first to get you to within 10, 15, 20 degrees of that. And then finally, you do a little bit of lead compensation to give you an extra little kick of an extra 15 degrees or whatever to get you to hit that spec. The only thing, and that's the approach for all the cases we're going to talk about. The only thing that differs from one amplifier to another is how do we do this? Basically, where do we put the cap? Okay, and how do we do this? How do we stick in the zero? Right? And for different, basically it'll amount to usually sticking a resistor in series with a capacitor, introduce a zero. So that's what we'll talk about.